how do we know that a chemical reaction has happened? If you see like a flask with some junk in it, how do you know that there's a chemical reaction occurring versus just a physical change of somebody stirring something or ice thawing? Well, there's some indicators. You can see that the color changes sometimes in chemical reactions. Sometimes a solid forms or precipitates out. Sometimes bubbles form. Sometimes heat or flame is produced, or heat is absorbed, aka it feels cold. These are indications of a chemical reaction. They're not foolproof, though. So ice is cold to the touch. If you touch it, you're actually heating it up with your hands, and it melts a little bit, and that's a physical change. So none of these things are terribly great in terms of telling you whether or not a chemical change has happened. They're nice indications. They are something that can like lead you on that trail, but they're not perfect. So indicator, yes. Like sufficient evidence, no. Chemical reactions, what are they? They are the scrambling up or the modification of existing bonds in the reactants to make products that have the same elements which are bonded together differently. So there's a change in the bonding. That's what a chemical reaction is. We don't actually make or destroy or transmute the elements in a chemical reaction. Mass is conserved, and what goes in the reactions must come out. So if I have hydrogen that goes into the reactions, you would better believe that there's going to be hydrogen coming out of the reactions. Okay. Here's a lame example. I mean, this concept, these ideas, are actually very simple, and I'm probably confusing a lot of you because I'm going to end up using a lot of like symbols from the periodic table, and it looks like, you know, alien garbage, or Greek, or I don't know, ancient, you know, hieroglyphics. But we can use examples from everyday life that you're probably very annoyed by, and that'll make things more familiar. So you could think about the packaging of hot dogs and hot dog buns as being bonds, or an analogy for bonds. So when you go to the store and you buy hot dog buns, you can get ones in like packs of 10. That's what you start with. And with bread, you start packs of 8. So if I was to make hot dogs out of like hot dogs with the frank and with the bun, I would need both like an equal amount of those franks and those buns. So I'd actually need to have 4 equivalents of those packages, of those hot dog franks, and 5 equivalents of those hot dog buns to make 40 total hot dog bun combos, like the thing you eat. So notice how I didn't actually destroy any hot dogs or any buns. I didn't eat them or throw them out or anything like that. If you count, I had 4 packs of 10, so that's 40, and I had 5 packs of 8, so that's 40 also, and I have 40 franks and 40 buns. So I didn't actually destroy anything or create new hot dogs. Everything's accounted for. Nothing was really created or destroyed. Just the way that it was assembled or associated with itself was changed. Here we have the chemistry version of the same concept. So this is the oxidation of methane. The black ball is carbon. The white ones are hydrogen. The red ones are oxygen. And you're looking at a methane molecule, CH4, being reacted with 2 equivalents or 2 molecules of O2. Those are those red dimeric things. The arrow means yields or creates or generates, gives rise to, lots of words for going from reactants to products. It creates or generates CO2, that's this one, and it also creates 2 equivalents or 2 molecules of H2O. So chemical equations show you a lot about what's happening. It tells you which are being destroyed and which ones are being created. It shows you how much of each are being destroyed and how much of each are being created per reaction. It's kind of like a recipe. It shows you the ratios of things. there's a decent amount of information here, and that's what we're going to spend a lot of time on it. You're going to become experts at it. So just to reiterate, here's that same reaction, which is not balanced in this slide, but we'll get to that in one more slide. I just want to reiterate that the reactants are shown on the left of the arrow. They're what are consumed as the reaction goes. There's an arrow that shows the reaction. It symbolizes that you're changing how things are organized here into how things are organized in the products. On the right, there are products, and yeah, we're going to look at how we're going to balance this. So the way we balance these reactions, once we know what the products and the reactants are, is we add stoichiometric coefficients, or we also could call these equivalents. We could even call these big blue bold numbers number of molecules, or like a ratio, whatever you want to call it. It just tells you in the recipe how many O2s it takes to consume one methane, how many O2s it takes to produce one CO2, how many O2s it takes to produce two H2Os. And by having these coefficients in front, by telling you how many equivalents or what the ratio is for oxygen, it allows you to demonstrate, like through just a little bit of math, that this reaction is currently balanced, that the number of elements in these molecules are the same for each and every element as the number of elements over here in the products. They have to be, or else it's not balanced. That means we have more work to do to get it to something we understand. You'll see in a lot of these reactions that we've put a state symbol. G means gas. Methane's a gas. OK, so just to color code this, that 4 in front of the aluminum means that there's 4 atoms of aluminum. I put a lot of work into this slide, so I hope you guys like it. Like that 3 in front of the O2 means that there's 3 equivalents of O2. So what I'm trying to say here is that the stoichiometric coefficients, the numbers that determine the ratio of the different elements that are consumed and the elements that are created, those numbers can be verbalized in different ways. You could say that, OK, there are 4 atoms of Al for every 3 molecules of O2. Or you could say that there's 4 moles of aluminum to every 3 moles of O2. And yeah, I know we didn't cover moles yet, but we will. It's a counting number like a dozen. So we could also say that there's 4 equivalents of Al for every 3 equivalents of O2. The arrow, again, I'm just repeating myself. It's boring and I'm in monotone, but you're getting it. I could say that arrow means gives or yields or generates. It's just showing you there's a reaction that changes stuff on the left side to stuff on the right side, from reactants to products.